Hey guys, hope all of us are doing fine. My name is Ernest and this is Ernest Sciences and the Mathematics TV channel. In this particular discussion, I'm going to look at the molecular partition function. And of course, this is going to be complementing on the previous video we have done on an ideal gas over atoms. Now, from that particular representation, we have decided that we can consider the energy of an individual particle perhaps given as a... So let's have this particle given in terms of what I... And this particle can be an atom or a molecule, but for this case, we're going to consider that this specific aspect, and therefore it's going to lay a basis for us in understanding the representation of a molecular partition function in that particular order. So we said that we can give a specific state of this individual particle in terms of a V. So we have the state of this specific particle in terms of a V, and therefore we can represent the total internal energy of that particular state by having the internal energy represented in terms of this specific state of this particle given as a U, V, I. And therefore, if we want to have a summation of all those states of energies, we said that we can represent molecules and atoms in terms of, especially gases, in terms of various states, whereby we're going to consider the aspect of a translation, vibration, perhaps rotation, and electronic state. And in this case, I'm going to consider the general case for various states and have a general representation, and therefore that's going to assist us find a way of representing this molecular partition function. So we are going to represent the various states of this specific atom, and perhaps we can give these states in terms of numbers for the first state, the second state, up to a state of n, and that's going to represent the total states of those specific individual states of that specific particle that I've given in terms of I. So if we consider an atom, then therefore we're going to have this general representation for the total states of this particular atom using the individual energies for the first state, and then we are going to have the second state given as such, and that's going to go on up to a particular state of the last one, which we are given in terms of n given as such. Therefore, we can have a general formula to represent this internal energy of this state, which is going to be a summation from I is equivalent to 1 to the n state, which we have given in this specific range. And this is going to be the total representation of those various aspects of the energy we have given, being given as I above of this particular particle. Now, for an ideal gas, we stated that basically we are going to consider the aspect of an ideal gas whereby all atoms are going to be considered to be independent. And of course, from the molecular kinetic theory of gases, we said that an ideal gas is one in which the energy of every component of an atom or a molecule is going to be independent from the others. So we said that in representing this, we can have the internal energy given as a kinetic energy. And of course, we're going to see that this can be given in terms of a partition function of individual energy states being described in terms of these individual states which I've given for UV1 up to UVn given as such. Now, in our last discussion, they're given a general representation for a partition function of an atom, whereby I'd said that this basically is going to constitute two states, either for solids and solids, liquids and gases considered together. And I'd mentioned the aspect of one whereby we're going to have all the atoms being the same and having a partition function for each atom being represented in terms of so Q, which is a summation of this specific state of U, the exponent. So we had this specific representation from the general partition function of B, but this is state of an atom, and therefore we're going to represent it using this specific aspect of V, which I've given. And this is going to be given as raised to power n. So therefore, from this one, this is a partition function, which is a Q, implying that the total partition function for this specific atom can be considered as Q raised to power n. And this is for what we refer to as distinguishable particles. Now, they said that we're going to consider liquids and gases as one homogeneous block in terms of the characteristic of particles. Since we're going to see that liquids and gases are going to have particles which are going to exhibit the aspect of swapping or moving from one position to another, But for solids, we're going to have their individual particles, assuming a particular lattice where we can locate a particular particle. So in order of description of particles, perhaps for its vibrational state, we're going to locate a particle at a particular position. Therefore, we're going to have two representations for this partition function for liquids and gases using various aspects of either distinguishable or indistinguishable particles given as such. So for the partition function that we have given for this particular representation, this is going to represent solids which we have said having distinguishable particles. Now for indistinguishable particles like liquids and gases, we're going to have another version of this represented as the Qn all over n factorial, and this is going to represent their partition function given as such. So these are two representations for solids and liquids, or distinguishable and indistinguishable particles in that specific respect. So therefore, from that one, we're going to look at the concept of molecular partition function of perhaps gases, and we're going to consider the concept of an ideal gas in trying to represent this specific aspect. So we said that molecules and atoms, of course, or molecules of an ideal gas are going to have different types of motion. And the first one we had mentioned was the translation, which we can give in terms of T. And then we had said that we can describe the rotation aspect of this, or state of this specific atom. And therefore, we are going to have also an energy due to vibration aspect of this atom, and that's going to be represented in terms of V, and then therefore we can have electronic energy, or the energy due to the electronic aspect of that specific atom given in terms of E. So these are various types of course, states that we're going to have, or types of motion that we're going to have in describing a molecule. So suppose we have we assume that these four different states for describing a molecule are independent. Therefore, we're going to have all of this representing this aspect of the total energy, which I've already given in terms of an expression. So therefore, we're going to have this one given as UV is equivalent to the energy due to of this state due to translation, plus the energy of that state due to rotation, plus the energy of that state due to vibration, plus the energy of that state due to electronic or the energy contribution due to electronic in that specific respect. Therefore, the molecular partition function is going to constitute these various ranges of energies, and we can represent this one in terms of a partition function by having this one given in terms of Q is equivalent to the summation of these different states, and then we're going to have the exponent of negative B given by those various ranges of energies for translation, vibration, rotation, and then lastly we're going to have electronic given as such, and this is going to be the general representation for the molecular partition function of that specific state. Now we're going to use the concept of logarithms as well to try and evaluate this specific state for the molecular partition function, and of course we're going to use that aspect of addition, whereby we have said that if we have the natural logarithms of this specific exponent of A plus B, this is going to be given as the exponent of A times the exponent of B given as such, and of course that's going to be form a basis for our simplification of that specific representation at the lower part. So we're going to have the molecular partition function given in terms of the summation over this B to the exponent of negative B and this Vt, which is basically representing translation, and then we are going to have the summation from V of the exponent of this particular type of energy due to, so this was translation, vibration, and then we're going to have rotation, and then we're going to have this one given as times the summation of that specific state of energy due to U, V. So we have had translation and rotation, so we're going to have vibration, and then we're going to have this one given in terms of the summation of the energy given as an exponent negative, that specific notation due to electronic given as such, and that's going to form of course a range of energies which we can describe in terms of independent states for translation, rotation, vibration, and of course electronic given as such. So all of this is going to give us a sum of this specific representation, whereby we're going to have Q represented as the energy due to translation, the energy due to rotation, times the energy due to vibration, times the energy due to electronic given as such. And this is going to form a molecular partition function of a Q equivalent to Qt, Qr, Qv, and Qa respectively. So that's how we can represent a molecular partition function of an ideal gas given in that specific order. So kindly check our description boxes for various links of other videos, and our comment section and the description boxes for the link which I'm going to put there for similar videos. So that is it for now, guys. By God bless you. Catch us in our next video.